Hello, everybody. I would like to welcome you on our webinar today, focused on correlative AFM and SEM imaging and data processing. My name is Jan Neumann, and I'm CEO and co-founder of NenoVision company, where we focus on development and production of AFM system for SEM. We have decided to organize this webinar together with the company Digital Surf, and we have invited Arnaud Vignon, who will talk about the processing of correlative imaging. Arnaud, if you can introduce yourself a bit.
Yes, good morning, everyone, and welcome to this Mountain Speed version 8 presentation. I'm Arnaud Vignon, Digital Surf Sales Director, and I'm passionate about mountains, and I want to share my experience with you. So, thank you, Jan.
Yeah. Thank you. I would just to add several technical points. So webinar is live, and we are encourage you to raise the questions anytime during the webinar via Q&A window. My colleagues from NenoVision and also Digital Surf will try to answer your question immediately via chat, which is visible for everybody. And by the end of the seminar, we will answer some of them loudly. There is about 30 seconds delay due to the broadcasting, so just please be aware about it. And now I will start with the webinar. As mentioned, focused on correlative AFM in SEM imaging and data processing. I will, as we mentioned already, but I will talk more about AFM in SEM and how to acquire complex data for characterization. And later on, Arnaud will show you how you can process the data within the Mountains software. On the beginning, I will introduce a bit the company, also instruments, and I will focus on the data acquisition, and then I will pass it to Arnaud. We'll have some short summary, and then on the end, as I mentioned, will be a Q&A section. NenoVision company is located, we say, in the heart of the Europe, in the Czech Republic, in Brno. We are technical spin-off founded in 2015, and what is interesting about the Brno, that we are quite well known as a center for electron microscopy. It says that about 30% of all electron microscopes are produced here in Brno. Here's a Thermo Fisher facility located here on Soutescan company, and we have several exceptional universities. So this is the environment where we are coming from. What I will talk about is AFM module for SEM, and the instrument, we call it Lightscope. It's a specifically designed atomic force microscope, which we integrate inside to the SEM chamber. And simply, we try to merge the forces of both the AFM and SEM systems. Just very shortly, why we combine these techniques together, because they are complementary, and each of them is offering advantages compared to other. So we take the best from AFM, which is very precise 3D topography. You can analyze mechanical, electrical, or magnetic properties. And then we combine it with the possibilities of SEM, which is very fast 2D imaging, where you can also do chemical analysis, or you can modify your surface. Introducing the Lightscope, we make the short video, which is, I would say, the fastest and most educative way how you can gain information. So just let me play it and enjoy it.
The growing need to characterize and analyze structures in the nanometer range and the complexity of such measurements with various instruments create a demand for automated solutions in advanced correlative analysis. That is why we have developed Lightscope, a unique compact atomic force microscope designed for plug-and-play integration into scanning electron microscopes. With Lightscope, you are able to merge the forces of the two of the most used techniques for sample analysis on the nanoscale. Measuring with Lightscope is intuitive and simple, yet precise and time-efficient. Its integration into the SEM prevents sensitive samples from contamination or oxidation, as the measuring is done in the same place and under the same conditions. Lightscope enables precise localization of the region of interest and AFM tip navigation. It extends the capabilities of SEM by measuring a sub-nanometer topography, together with mechanical, electrical, and magnetic properties of the sample. Lightscope incorporates a unique imaging technique called correlative probe and electron microscopy, shortly CPEM, enabling simultaneous acquisition of AFM and SEM data. Lightscope and the CPEM technology allow sample analysis in a way that was difficult or impossible by the two imaging technologies separately. Together they bring new possibilities for advanced correlative imaging in a variety of scientific and industrial fields such as material sciences, nanostructures, semiconductors or solar cells industry, life sciences, and many more, defining their own category of the correlative microscopy.
So this was a short introduction of our instrument Lightscope, and now I would like to tell you a bit of more how actually we integrate it and how we connect it to the SEM. What you see on the picture on the left side is the SEM, and inside you see the Lightscope measuring head. Then you see the feed-throughs and the cables which are connected to our control units, which we call NanoBox. On the right side on the screen, you see the NanoView. As you can see, there is no actually additional PC to the electron microscope because our software is running in the web browser. So you just put the IP address and you don't install anything, and you can run the NanoView. What is actually missing here is also part that we are directly connecting the signals from the different detectors from the electron microscope, and we connect them directly to our NanoBox unit, which means we can control and acquire all the data together. Now I would like to just shortly highlight a few field and advantages which we see in combination of AFM and SEM. First of all, we are driven to the complex sample analysis. What do we mean? We have a unique method for multi-dimensional correlative imaging, which we call CPEM, I will talk about later, which enables the simultaneous data acquisition of both SEM and AFM data, and then their merging. If I would like to give you the example, here's an example of 2D materials, molybdenum carbide, and this is visualized by the SEM morphology. When we talk about the complex analysis, what we do is we add the additional information from different techniques. So from AFM, we added topography. We add there also information about the mechanical properties. We can use EDX, for example, to add their information about the chemical composition. And by the end, we want to correlate all of them together, and this is what we do in the CPEM, simply multi-dimensional correlative imaging. The second very important field is so-called in situ analysis. Since we integrate AFM inside the SEM chamber, and then you can use the advantages of the measurement on your sample at the same time, on the same place, and under the same conditions, preventing any need for sample transfer or avoiding the sample contamination during the transfer. I'm very happy that for this field, Mark Willinger became our scientific ambassador. Mark is from ETH Zurich, and I really do like his claim that Lightscope is like Swiss Army knife inside your SEM. Simply, we are bringing many additional functionalities into that. The third very important area where the combination is advantage is a ability to precisely localize the area of interest, because you are using SEM to navigate your AFM tip to the exact location and where you can further make the AFM analysis. This is not possible with the conventional AFM because you are missing the SEM detail and SEM view. AFM is actually bringing into the in situ SEM analysis many properties. We are bringing to ability to measure, analyze many properties. So the one of them is the mechanical properties, where we can analyze the topography with sub-nanometer resolution. You can measure local surface roughness. You can measure elastic properties or surface hardness. Also, we can analyze several electrical properties. So you can do local conductivity map, or you can measure surface potential using so-called KPFM technique, or simply you can measure just IV curves. We can perform the analysis of magnetic properties using MFM techniques to visualize the magnetic domains on your sample. And we can measure also so-called electromechanical properties using analyzing the piezoelectric domains on your sample. So as you see, there is a whole branch of analysis which we are bringing to SEM community. There is also several areas, application areas, where it's highly advantage to use that. Most important is, I would say, material science, where we have plenty of applications in 1 or 2D material analysis, steels, metals, or in battery or ceramic research. Also, very useful is AFM for the analysis of nanostructures, which are, for example, created by focus ion beam or gas jet injection system. So then it's suitable for quantum dots, different nanopatternings system, etc. We have several applications also for semiconductors, mainly dealing with the failure analysis, where we are locally able to visualize the current leakage or dopant visualization. And last but not least, the area of life sciences, where we can analyze different cells or proteins, and we can add there a lot of information. I would highlight the correlative data acquisition and our unique CPAM technique, because this is what you will see how to work with them. So if you want to do the correlative measurements, so you need at least 2 different images or 2 different channels which you can correlate together. And here we are nicely utilizing both AFM and SEM, and we are introducing the correlative probe and electron microscopy technique, which is CPAM. So what we do, as we have an AFM tip, we focus the electron beam very close to the AFM tip, and then we start to scan with the sample. During the scanning, we are simultaneously acquiring the data from the SEM, from the different detectors, and from the AFM. And because this is the same scanning system measured on the almost same place, it's very nice and very straightforward correlation together. What we do then during the data processing, we take the best from all of them. We use the AFM for the really nice and precise 3D topography, and then we take the signal and contrast from electron microscope and we put it right on the as a mask on the 3D topography. And this is it. The result is, we call it CPAM view, which combines information from AFM, which you see in the topography, and from the SEM, which you see in the color. But as I was talking about the multi-dimensional data, we can simultaneously acquire more channels. not only topography and secondary electron, but as you can see, we can simultaneously collect also backscattered electron data and then merge everything together. With the CPM measurements, we are really highlighting and taking the advantages of both. Here is one example. If you compare simply AFM data, topographical, and then if you compare it for the CPM data correlated with the information from electron microscope, you see you are adding the completely new layers and new informations coming from separate techniques. I just wanted to show you how we acquire the data. So on this video, you see how we set in our software different channels. Each channel is representing different signals from AFM or from the SEM. And then during the scanning, we are simultaneously acquire all of them. So as you can see, we have all of them in one in our software, and then it is very easy and straightforward to process them. Currently, what I'm showing here is a topography AFM data, secondary electron data, backscattered electron data. Also, there is a local elasticity and error signal. So this I wanted to give you idea how we are able to collect all of the data simultaneously. And now I will just shortly introduce examples which will be then proceed and show you in more details during the talk of Arno. So we select two samples. One of first of them is grain of M3 high-speed steel. We simultaneously collected 5 channels, and actually you have got the data, so you can check. You see their AFM topography. You see differential topography, also so-called error signal. You see energy dissipation, which is equivalent to local elasticity. And then you see channels from secondary electron and backscattered electron data. You see each of the channel looks a bit of different. And then we will show you how using the mountains you can analyze them. The second sample we picked as a 5th mil nanostructures. The reason is because they are regular, so then we can show you some advanced tools. And what you can also see, which is quite typical on the AFM topography and SEM data, you see a bit of different images. On the SEM, you see a really nice contrast from the gold covered areas, which are not visible in the topography. This is typical situation where you see something different in topography or in different channel than from the electron microscopy. So this is really nice and important to put them all together and gain the informations about your sample. So I would try to sum up the benefits why to combine AFM and SEM. First of all, we enhance the capabilities of electron microscopes, bringing the AFM technique inside. I wanted to show you that we have an ultimate precision of the correlative imaging. Also, you will see during the data processing, and this cannot be done by subsequential acquisition of data. Is done because of the simultaneous acquisition using same scanning system. There is no risk of sample contamination because there is no sample transfer between the AFM and the SEM. And I would like to stress out once more the very simple and fast localization of your region of interest. And what I like to say, we are bringing the third dimension to the electron to really nice 2D SEM images. With that, for now, thank you for attention. And I would ask Arno to take over and continue with the data processing of these samples.
Thank you very much, Jan. It's very impressive. Great. So I will share my screen now. Can you see my screen? I guess yes. So Digital Surf produced mountains for more
Arno,
than
I'm sorry, we
25
don't see your
years now.
screen.
And Mountains is a technology name for
Arno,
different type of softwares. We
Arno,
have application for scanning profilometry. We have
Arno,
application for electron microscopy.
Arno, you are not sharing your screen.
Okay. Sorry. I'm sorry. Okay.
Yeah.
Let's go again.
You see this live?
Yeah. I'm just trying to share my screen now. Can you see my screen?
Yes. Thank you.
So this is Mountain's screen now. Can you see my screen? So Mountains, once again, Mountains is a technology name for a series of software. The application is scanning profilometry and microscopy profilometry. We have also 2D profilometry and aerial surface analysis. We have electron microscopy application. We have scanning probe microscopy application, and we have a spectroscopy application. So altogether, we can do also correlative analysis between different domain of applications. So we have a segmentation by type of hardware. With NenoVision, we are going to show you Mountains PEEP application for scanning probe microscopy application and for correlative analysis with scanning electron microscope images. So here is my Mountains PEEP user interface. Actually, I have already customized my interface with my preferences. First of all, I can go to the file preferences and would see what kind of preference I like to use. For example, language be selected by the user with those technologies. We also have some preference for metrology with filterings, and we have a long compatibility of file formats for different type of application. The SPM application, but also in some other domains of applications. So here is a document with the dataset load by the image came from NenoVision. The dataset came from NenoVision. We call it studyable. So I already load this studyable containing 5 different channels. The topography from the AFM, the frequency error for the AFM, the excitation amplitude from AFM, and also the scanning electron microscope image and the BSE image. Those images are converted as an intensity image. So this is the file here. I can do it full screen with FL11. So you can see the different channels with palettes for the different layers. So as you can see here for the this layer, the BSE, I use a very limited rainbow palette to be interactive with the user. You can change the colors as you wish, and you can see the different domain of material with the BSE image. With the topography, you see a conventional palette here. And as you can see, before this view, I was using a leveling option. So if I double click on this summary operator, I can reopen the user interface and see what was the prediction of this leveling. So in this case, I was using an automatic fusion to compensate the height level by 0 here, and the result is here. the single topography was delivered by this method. The following image, the 3D view, is more impressive, I think. And once again, I can use in this interactive ribbon, I can use the full screen display here to see my surface live. So I can zoom in with my mouse and rotate with my mouse. Actually, I don't use a mouse. I use a touchpad from my laptop. It works as well. And I can change the layer as I wish. What you see here actually is the topography height, the elevation, and here I can superimpose the BSC information. So you see a topography with different sort of different kind of material. Of course, with the topography here, the simple topography view, you can select your preference and your preferred palette. For example, I want to use a rainbow palette like this, and I want to highlight my palette by sorting. That's really view. So we have a very nice engine to display the topography and to see the different channels in once. The following steps is a profile. And as you can see, it's a multiple profile. So I did an extraction across the surface. You can see the slider here. And actually, in my user interface, I have this tab here, workflow. It gives me the document contents. So it's a very simple contents. You have a labeling and you have a profile extraction. If I click here, I can see my profile extraction. And I can move my profile extraction where I wish. And I extract all layers in once, which is the view you have here. So you can see the different components here. So I can display all of them, but in this case, it's a bit busy, I would say. So I just remove some of them and to compare one versus another one. And you have the corresponding layer information here. The following steps is a particle analysis, which is a very important section of the software. So the particle analysis consisting of particle counting and detection and counting, I would say. And you can select the detection with this view here. As you can see, you have the different layers of the surface, and I was using the layer number 5, which is the SEM BSC layer. So I use a BSC to detect particles, and my detection is based on a threshold method. So I was using these two threshold limits to isolate the peak here for the detection. And then the calculation layer is the layer number 1, which is the topography. So my wish is to have calculation of the volume, for example. So I can sort my grains and particles with the volume information. And for example, I can click on this one and I can directly read the volume and some other factors of the particle. As you can see, there is a lot of particles because in this case, I have a large density of particles. I have 27 in this image, but the particles by square millimeters in the range of 36,000 particles by square millimeters. So the following slide here is statistics based on the particles analysis. And here is different view of statistics summary, which is the summary of all particles detected in my image, in my previous image. I can see a control chart which is the numbers of the particle here versus the volume of the particle. I have an histogram of distribution with respect of the class. So I have to show you the class sorting here. As you can see, in this example, I have three classes, A, B, C, based on the volume analysis. So I can see the particular classification in this icon here. So I have three classes based on the volume information. Eventually, I can create a new class to detect a very big one, I would say. So I could be a dark color like this. And eventually I can change the sorting of my classes. This is, and as you can see in my document now, if I look at the classification, oh, sorry. If I look at the volume here, I can see the different classes in my histogram and so. So this is the first document here I have. The other document is about the nanostructures. So the nanostructures given by NenoVision hardware. It's very nice. So in this case, I was using two operators. You can see this in the summary of operators. The document pages are here. And I can recall the operations by double clicking. For example, here I was just sectioning field of interest, and I was isolate and take this as the region of interest for the two layers. So I have two layers in this two channels in this example here. I have the topography, and I have the SEM image, which is now colorized with a rainbow palette. Once again, I can change the settings for the view. The other operator is leveling. So I was using a 3-point leveling just to ensure that those parties in this image are on the same level. The z-axis now is the 0 is the average of those 3 points. The following step is the 3D view. And make it in full screen mode again. So here you see the different sectors given by the BSC formation of the electron microscope with the topography view. So the topography is here, and the topography with the BS color is here. So the amplitude is set by the user, because actually, if you look at the layer here, the topography, the height is very low, in a range of half a micron height. So the amplification here could be given by the user as he wish. So in this case, I was using a strong amplification, but usually we use maybe 8, 9, 10 percent of amplification. But in this case, we can magnify a little. It's impressive. So the following step is height calculation. What you see here is the histogram of distribution of the height. So the vertical axis is the height, the Z height, and the lateral axis is the percentage of the class. This histogram could be displayed like this, or in a 90 degrees view as well. You can select this as you wish, vertical pins or horizontal pins as you wish. This histogram is used to detect different steps on this object and to calculate the elevation of each planes. As you can see in this example, you have 3 planes, the blue, green, and red, and the detection of the planes is available here, multi-plane analysis, and you see the software calculates the average height of this red section of pins, the green, and the. Of course, the user can set this analysis as he wish, and you can do also manual method of norm calculation as well. So in this case, you have some option to display interesting measurements, the height, of course, but also the angles different in the different planes, and maximum amplitude and distance. As you already know, I can extract a profile here, combining the height and the SEM information. So the next and the next slide, the slices, where you can calculate some percentage of surfaces here and the volume of corresponding slices. So you can do with 1 slider or 2 sliders. This is for the volume calculation, and here is a volume given by the user selection to calculate 1 cell volume. Of course, some analysis could be documented. So, for example, if you want to know some information about this calculation, you can press F1 and then you get an interactive help menu of the software. It's also contextual. If I change my view here to slices, if I press F1, I have slices. So the help here contains up to 800 pages of information. You have everything in this. It's great. You also have parameters information, and I wish to show you how it works. So, for example, here I have a threshold, and the threshold isolates the top surface of my thing. So I can see the bearing surface of the top, and based on this, what you have in gray is not measured, so only the colored part is measured, and the parameters are calculated on the colored parts of the image. The other points are missed, I would say. So Mountains is fully compatible with non-measured areas, and as you can see here, it's easy to isolate some region of interest. The parameters here are coming from the norms, the ISO norms, the ISO 25178. And if you want to know some information about those parameters, you press F1 and you get a very complete information about the parameters, the method of calculation, and also the norms information and how to use the tables and parameters selection and so on. Of course, this tab here is also interactive with the user. And for example, you can select some more parameters here. Or you can remove some parameters. So this is a list of parameters you can select. You have a lot, as you can see. And if you want to simplify your document, you can remove some of them, for example, and just take the best one for this surface. Oh, I'm sorry, it's time for me to demonstrate how to create a document. So I want to make a new document based on the file, the given file. So I start from 0 here. I just use my File Explorer to select a new file. And I see here a two channel file. And I load the file here. I can load it in the document, or I can create a new document. In this case, I can continue my document with a new file. Why not? So in this file, as you can see, there is a need to compensate the flatten operation. So I can use a quick operator to make it, so which is a line leveling. This is the result here. And again, if I want to see what the leveling was, I can go in my workflow and select this operation line by line, and I can see the settings of this line correction. So I was using degree of 1 with an automatic surface extrusion, which is points here, and the method is based on the line leveling, which is very efficient for this surface. So now I can see this surface in 3D view. It's flat. So eventually I can change the palette as I wish. And for example, take this one as a basic one. And I want to add a color for some reason. So I can double click my palette and say I want to add a dark color here. And you can see the new color combined with the other color. Okay, so that's a nice surface with some particles. And now I want to calculate some parameters on the particles. So I go to studies. The studies allow me to calculate some parameters. You have a long list of parameters, as you can see here. And the relevant one is particle analysis. So this is my default calculation here based on the edge detection. Actually, this is not exactly what I want to make. My preference is to use another method, which is a circle detection. And fortunately, I have as a previous setting information here the circle detection. It's a shortcut to or one-step calculation of the circles based on the previous settings I did for a similar application. So the circle detection here, information is available here. So I have several parameters to detect the maximum and the minimum diameter of the circles, and then the segmentation is based on this threshold here value and the number of minimum pixels. Here is the result, and you can see the information of each particles. Once again, can go to the classification, and you can change the class class, and you can eventually add a new class. It will be in green, maybe. This one I can set because yellow is difficult to see the difference. A light color like that. So now you see different information, and eventually you can see the different classification. For the classification, I can say it's not a default one, it's based on the volume. So I say here. That's the thing here. The volume information, I can classify the volume from the smaller to the bigger volume. So red is a small little volume. Okay. And now I can use my calculation and my results here to create some statistics with this chart here. This is the volume, but also some other parameters. This. So I have a summary here of some parameters. Statistics could be selected here. I can add some statistical parameters if I want to have a view here. And of course, I can see some other way to display statistics, like the box plot here, which is nice to see. Oops, sorry, I have to click OK. So the volume with 4 classes, you see some information about the average value for each classes. If you need some information, please press F1 and you get the box plot information for the statistics. You have the information about it here. Okay. And you have a lot more features on this type of surface. And use another operator to create a new study. For example, to extract a profile, you can use this icon and say, I want to extract a profile, and you can select the profile as you wish, eventually a very complicated one. You can select a multi-layer profile or a single profile. So here I just want to extract the topography. And on this topography, I just want to know some parameters about studies about roughness, equation, and maybe spacing parameters as well. So I have my parameters here, and spicy. So Mountains SPIP offers a lot of flexibility for the user to calculate everything, and you see now my workflow contains a lot of information here about the document. Once again, the document was once based on the NenoVision dataset. Then I just use another surface to calculate parameters on the surface, and everything is in this workflow and contains the full interactivity with the user. If I want to change the profile extraction, for example, I just have to click here and say I want to make an extraction like this, and now the calculation on this profile is available here, and the calculation has been updated with the new numbers. It's time for me to switch off my voice and to allow you it's time for you to test Mountains. Actually, you can download the software and you can make some trial. And please ask your question to NenoVision or to Digital Surf support at digitalsurf.com if you have some technical information about the software.
Thank you very much, Arno, for a really nice presentation and talk about the mountains and how to work with the data. I think it was really nice and useful for everybody. So let me summarize this webinar. It was composed from 2 parts. The first, we were talking about Lightscope, our AFM system for SEM. We wanted to show you how we are doing simultaneous data acquisition using the CPAM, which we see as a next level of correlative imaging, especially for the precision or correlation, and simultaneous in situ data acquisition. I wanted to inspire you that the main application fields are material science, nanostructure, semiconductor, and the life sciences. And we wanted to show you how simple it is to acquire multidimensional data. Arno was showing you quite a lot about the image processing of correlative and multi-dimensional data on 2 samples, and also he showed you some tips and tricks how to do some AFM data processing. I would like to remind you one more that on the invitation link you can download free trial of mountains. You can download the set of the data which we were showing here today. So feel free to use it and try yourself how this combination can help to your research. With this part, I would come to Q&A session. So it was quite several questions during the webinar. My colleagues, I think, were able to answer most of them. So what we did is we picked a few of them, which we think it makes sense to let me answer them once more loudly. So I will do it, and the same the Arno will do it. So one of the question was, what's the maximal area the system can work with, and how long does it take to scan the area? So it's the scanning area which we are able to analyze is given by the scanner. So in our case, it's 100 by 100 micrometers. It's 20 micrometers then in the Z direction. And how does it take? It really depends on the sample which you have and the resolution, etc. The fastest scans which we are doing is about 2 or 3 minutes, but it might be also 20 minutes if you want to scan big area with really high resolution, etc. So yes, so I hope I was able to answer this question. The second question is coating still necessary for non-conductive samples? If so, will the coating change the sample surface features? So I think it's related to the coating of the samples, which is necessary to be analyzed by SEM, right? Because of the charging effect. So if you are looking from the SEM point of view, yes, the same is still is the same. If you want to SEM for analysis, you still need to code it. For the AFM perspective, it does not. We do not need that. We can analyze non-conductive samples. So if just the rough navigation, when even some small charging effect are okay for you, and then so then there's no need to code your sample. Will change the samples features? Of course it will, because if you will place on your sample 2-3 nanometers or gold or platina, so the first of all you modify a bit the topography. Then it depends what's the size of your features. If it's 200 nanometers, then 100 nanometers doesn't matter that much. If you are talking about 1 nanometer size particle, yeah, then it matters. But also you change the mechanical property a bit and you change the conductive property. So coating influence the sample. And it's needed because of the SEM. It's not needed for the AFM analysis. Next question. Would you please talk about the cantilever? Is it piezo-resistive cantilever? How do you code cantilever for applications like APFM, MFM, etc.? So that's right. We are using special type of probes and cantilevers, so we don't have any optical deflection. So we are using several types of self-sensing probes. One of them is Akiyama using tuning fork. Another type is based on the piezo-resistive cantilevers. This is right. And then there is several types of these piezo-resistive cantilevers. Some of them, they have coatings. Usually we use platina on the tip, so which makes them conductive. And then it's suitable for conductive AFM or KPFM, etc. And then for conductive, for MFM measurements, we actually use modified Akiyama probes, which are based on tuning fork, and we deposit the piece of iron on the very end of the tip. So I think the diameter is like 20 even less nanometers. So then we are able to make very precise and high resolution MFM imaging. But there is plenty of different type of cantilevers according to specific method which we want to use. Is it possible to analyze FIP lamella surface with the AFM, or are lamella too fragile? No, it's possible. We did it several times, because you can set the so-called set point, so the force, how much you are pushing to the surface. So for AFM, lamella is absolutely okay, and we can measure the surface roughness or even conductive properties on the lamella. So this is absolutely fine. Now there are several questions to mountains, so I would ask Arno probably to answer them. So Arno, if you can switch on.
Yes.
Exactly. Yeah.
My microphone is on now. I'm not sure is Mathieu already there. Maybe not. So I will reply to those questions. Interesting in using mountain speed. Could you describe the typical application of polar plots in the software? Does it correlate to relevant orientation? It seems a bit complicated to respond in 1 month in 1 word. So I'm afraid it's a very technical question that could be answered maybe a bit later, because we need to show you some typical applications, and I need also some examples of polar plots. So of course we can do some software analysis of polar plots, but we need some data sets. So if you provide us some data sets, we will be pleased to make it for this analysis. Currently only 2 Y-axis right. Is it possible to choose? Yes, actually, it's interactive with the user. You can extract multiple access, multiple channel files, and in such a case, you can isolate each profiles as a separate view, and in this case, you can mix. You can see different y-axis, different graph. If you combine everything in once, in this case, you mostly have the one-axis view on the document. As a software tools to deal with image alignment of the drift to SEM. That's a very good question. If I'm right, there is no real drift with the NenoVision dataset. I was using several images for trials, and all of them are very good quality. But if there is some case where you have a problem with the image linearity, if you have some difference of localization between two samples, yes, you can work on a new correlation between the images, and you can correct the linearity of the AFM channels if necessary. Once again, the NenoVision provides very good quality data set. What does texture direction tell us about the surface? Oh, actually, this surface texture direction is a method to calculate the isotropy of the surface. It's a very good question because somewhere, if you want to see the surface texture analysis, you have to know that the profile could be could give a wrong value of the surface texture depending the orientation of the profile extraction versus the isotropy of the surface. The benefit of the aerial parameters, they are not dependent on the texture direction. Methods are calculated in all directions. So in this case, there is no variation with the profile extraction direction. So the surface texture direction is a very important parameter if you want to know the isotropy of the surface. If you need to extract some profiles in one direction, if you have a low texture direction, it means that you have low isotropy, and then you can extract the profile everywhere. The reverse is not true. That's a good question.
Thank you very much, Arnaud.
Thank you very much. Yeah.
For answering your question. So with that, I would like to close the webinar and workshop. Thank you very much for your attention. I hope that you have learned some new things. It was fruitful for you. And please stay healthy. Contact us if you have any further question. Stay tuned and stay interested. Thank you very much once more. And thank you, Arnaud, for participating. Have a nice day.